Okay, so we've spoken about the natural numbers, and we said that the natural numbers are from 1, 2, 3 out to infinity. We spoke about from natural numbers. We did speak about rational numbers. No, we spoke about integers. Sorry, we spoke about the integers. We spoke about integers. So this was like n. We spoke about integers. This is z, and this was equal to from the negative natural numbers, including 0, all the way up. Then we spoke about rational numbers. Last week, we were introduced to rational numbers. Then we said that this was Q, and then you could write it as m over n, where m and n are integers, and n is not 0. Then last week again, you learned about complex numbers. You learned about complex numbers. So complex numbers, you saw that was something like x plus iy, where again x and y were real numbers, okay? So real numbers, and such that I squared is equal to minus. So you learned also last week a lot of stuff about complex numbers and rational numbers. Then we've learned about, so in this order, we actually see that we have the naturals are contained in the integers, which are contained in the rationals, which are contained in the real numbers, which are contained in the complex numbers. So we have this kind of relation on the number system, okay? On the number system, we have such a relation. Then we know of such certain algebraic operations. So operations that we know of have been addition, we know of addition, we know of subtraction, we know of multiplication, and so on. We've learned these things. We've learned the inverses in addition, the inverses in multiplication. Then we've learned the identity in addition, identity in multiplications, and so on and so forth. So these are things that we've learned over the course of the whole semester. We've gotten the ideas, and we've also introduced ourselves to these things. Today, we are going to talk about groups, okay? So today we are going to talk about groups. We'll talk about groups today. We'll talk about the three main objects. One is groups, the other is and then the final ones are fields. So these are the three objects that we are going to talk about. So we'll start with groups, okay? We'll start with groups, and then what is a group? It's a very good definition, but usually one of the things that I try to give is an example of where you can see a group, okay? So a group, practical application or practical or some very good example of applications of group. What a group is what we call the Rubik's Cube, okay? We have something we call the Rubik's Cube. Rubik's Cube. I'm quite unsure if you know what this Rubik's Cube is, but I think everybody has seen one before. Rubik's Cube is a type of cube. It looks like that. Okay, it's a cube. And then usually on this cube, sometimes it's you have it's divided into 9 or something like that on each face. So you have something like this, then you have something like that here, all the way. And each of the faces has these 9 elements. Sometimes they are colored red, yellow, green, blue, and stuff like that. Maybe I just show you briefly an example of a cube, okay? A cube, a Rubik's cube. Example is this guy. Can you see this guy? Okay, this is what we call a Rubik's cube. So usually you see that it has kind of colors: red, green, yellow, blue, white, that you try to make. It has also orange there. So you try to arrange this cube such that all the greens go to one side, all the yellows to one side, all the blues to one side, all the whites to one side, all the orange to one side. So this is what we call a Rubik's cube. So usually what happens is that you have such. So usually we have this Rubik's cube, and this is really a typical example of groups, okay? And we are going to explain what it means to have what a group is, and how we can identify these groups. All right. So if we say a group, then we mean something very simple. So I write for you the definition of a group. So if we say a group, and just writing from the book, from the lecture notes as well, is that we have a set, okay, we have a set G and a binary operation, okay, we have a binary operation. So this binary operation star, the group, axioms that follow, okay? If we have the following axioms that are satisfied. One, associative. So by associative, we mean that we mean A operation B, sorry, A operation B, operation C, where we put this into bracket, equal to bracket A operation B, operation C, and then for all A, B, C, okay, for all A, B, C in G, all right? Then we also talk about, then we go on to talk about, two is that we talk about the identity, okay? Identity. So for identity, say that if we have an element, okay, if we have an element, we have an element E, if we have an element E, okay, which belongs to G, which is a set, such that A operation E is equal to E operation A, which is equal to A in G. Well, then we say that this is an identity. Then third one, the inverse. So the inverse is such that if we have a also a set G, then there is an element. Okay, there is an element to power minus 1 also in G, such that A operation A inverse is equal to E, where E of course, is the identity, okay? Is the identity. So this is really the definition of what a group should be. It should satisfy these three purposes. So usually we write it as we have a set, and then we have a binary operation on the set. Then we say that it is a group if these three properties are satisfied. Okay, I'll edit. I'll check the writings again. All right, so I'll make it clear. So this is what we mean by what a group is. There are several examples. Okay, several examples. We'll prove one of them. Just the integer and then the binary operation plus. We also have an example of rational numbers and also binary operation plus. It's an example of a group. So it means that if you take this set, if you take the set Z, then you can take these binary operations. If you take this set Z, then you can have identity. You can have the identity, the inverse, and then you can also have associative properties satisfied in this on the integer number system. And of course, if you take the rationals as well, you'll be able to have them. So this is all that we mean. Of course, there are other examples like if you have zero without zero, then multiplication also will hold. If you have the rational numbers without zero, then if you take the multiplication operation, then you also have that it is actually also a group. So these are some examples of how group is. But then the question, how will you show that if we take this case, how do we show that this is a group? One, two, and three. How do we show that one is a group? So to show that one is a group, you need to make sure that you satisfy the axioms or the axioms that we just spoke about. So one is that you take one. Let's show one. Let's show one. Okay, let's take one. Let's take one. Sorry. Let's take this guy. Okay. So let's show this operation class. How do you show it? So first, we need to consider associative. Okay, one. So if we consider associative, you must prove that Z satisfies associativity. How do you do it? So it means that you take A, B, in set, then we say that, sorry, take A, B, okay, take A, B, and C in the set Z, then we say that A plus B plus C is equal to A plus B. And then if we put our bracket here, and then we put our bracket, you know that we have satisfied our associative property. Okay. Then the next one is that we need to show for the identity. We need to show for identity. So to show for identity, what do you do? Say that two identity. So to show for identity, we take an element of the set. C. We take an element A of the set. And then we also take and then we take and take also E also from the group. Then we can get the identity. Then the identity element, which is the identity element, and the identity element here. Okay. Then we say that A plus 2 is equal to A. That is what we know as the identity property. Okay. So if we write that, then we know that we can write A minus A. Okay, we take A to the other side. Then this gives us 0. Okay. So this is what we mean by showing that for that identity operation. Then here, the identity operation was this one here. Take this is the identity. So this is the identity. Sorry. Okay, this is the identity. So if you have any operation and you take A operation E, if you resolve it and then you take E operation A and you resolve it, you should A. So it is what we call the identity. So we go back and then we take addition, or we take the integer and we take plus, and we say that A plus E should give us an A. This is what we mean. And then it means that if we solve for this, E will give us 0. And the second part is that take E. So take E now. Take E now. Okay, take E now plus A, and that should also give us an E. All right. So there are two things. One is the left hand side, and then this is also the right hand side. You can call it. Each of them we should get an E. Let's pick the left hand side, okay, which is at E is equal to A, and then we find A. Then we do the right hand side. So the right hand side is E as this. If we resolve it, we have A minus A, which is also 0. Okay. So then it means that we have found identity elements. Okay, identity element. So we say that the identity element is 0. Okay. Okay, so if we go back, we want to show that. So first, what we do, we take that, we take the identity as well. Then the final part, which is the 3, is the inverse. Okay, it's the inverse. So if we take an element in the set G and we let the power minus 1 also in G, okay, being the inverse of A, then I'll write the following. Then say that A plus A inverse should give us the identity. All right. But what we know is that this identity is nothing but 0, because we have found identity in the second instance already. Okay, so in the second instance, we have already found the identity, and we know that the identity is. Now to find the inverse, we say that A operation, A inverse will give us the identity. We know that the identity in this case is, which is the identity. Okay, then now we find what this A inverse should be. So it means that we can just see that A inverse plus A is equal to 0. And then it means nothing but A inverse is equal to minus A. Okay, so in essence, we say that A is equal to minus A. Okay, means that every element of the integer set has an inverse. We'll always get an inverse. Okay, so if we can do that, then we know that set and then operation plus is a group. So it means that we can do the same for Q. We take Q, we check for associativity, check for identity of Q, and then we check for the inverse of Q. And then if we can find these strings, then we can say that Q and then plus is a group as well. Okay. Then the minor remark is that if you have a group, if J is a group, mute yourself. So do you see the screen? Can you see the screen? I need someone to write in the chat box if they can see the screen, the whiteboard that I'm writing on. Can you see it? Okay. So if you can't see it, then you have a problem with your settings. All right. So a little remark is that if we have a group, and then if we have G as a group or as a set in a group, and then this set is a finite set that consists of n elements. Okay, so if J is a group, sorry, G is a set. Okay, it's a set consisting of n elements. Okay, if you have n elements, then we say that G is a finite group. Okay, and has the operation also to it. If G, however, is infinite, then it creates, then we'll create an infinite group. Then we have an infinite group. Okay. So for example, if we write, for example, something like Z, and then we write plus to X, then we know that this is infinite. Okay, this is infinite. So we have created an infinite group. However, if we have something like J to be equal to 1, 2, 3, 4, and then we say that we have J plus, then if it is really a group, then we can limit ourselves and say it is a finite group because we have this. Okay, so but let me just say maybe this maybe J like this. So the question is this finite or infinite? Finite or infinite group? Okay, but you could see that during the definition of the group, one thing that we did not state was something on commutativity. Okay, so this is because, so I say we have for commutativity, for commutative group, or sometimes usually called abelian or commutative group, we say a group, okay, a group G prime is said to be abelian, okay, if the binary operation, star on G is commutative. So that is, by commutative, we mean that if we have X star Y, then we should get Y star X for all X and Y in G. That is what we mean by, then we have an abelian group. So abelian group is a group that is as well commutative. Then what are some properties of the group? Okay, of groups. Properties of groups. Properties of groups. So we list some the properties of the groups. One is that AB is equal to AC implies B is equal to C if A, B, C are all two, means that BA is equal to CA implies B is equal to C if A, B, C are all in G. And of course, the difference is that this is usually called a left translation. Okay, a left translation law. And then this one is called a right translation law. That is the only difference. The third one is, of course, the inverse. So we say that a minus 1 or minus 1 is equal to 2 if A is in. So this is how we find that the inverse of the element itself. Okay, the inverse of the element is the element itself. Then the fourth one is that if we have A inverse, then we write it as B inverse, A inverse, okay, which is the product, okay, which is the product, the inverse of a product. Let me write it. Inverse of the product. Okay, inverse of the product. So we can prove all of this for sure, and the proof is very, very straightforward. Okay, so I prove the first two for you, and then you prove the rest of you check the proof of the other ones. So I prove one, that suppose we have A, B, C, or A, B, and A is equal to B, and so let me write it again. So if we have AB is equal to AC, okay, then B is what? AB, and then because we know that this is the identity. So the identity is nothing but A inverse of A, okay, times B. This is nothing A inverse of AB. You can rewrite that. And this is nothing A inverse of AC, because we are saying that B is equal to AC. So A is equal to A inverse times into bracket AC. And then you can rewrite this again. You can rewrite this again as A inverse A of C. Okay, and then we know that again A inverse A is the same as E of C. Okay, which is nothing but C. So for me, what we said was if we have AB is equal to AC, then it implies that B is equal to C. That's what we said. So this is how we prove it, right? You say, okay, B is equal to, we can use identity product identity as this, and then we can write the identity as an inverse, and then we can rewrite expand this and change the associativity, use associativity. So it's very, very critical you understand. So here we use identity. Here we use the inverse, okay, the inverse as means to the identity. Then when we come here, so then we come here. Then here we use associativity. Associative, right? Then when we do associative, so no. So from here to here, okay, yeah, we do associative. Then here to here, this part, what we then do is substitution. Substitution. Okay. And then once you do substitution, then again, you apply at this point associative again. And then when you do associative again here, then you use the identity to give you the results that you need. All right, then the second one says that BA is equal to CA and implies that B is equal to C. Of course, I'm not going to do that one because it's very, very straightforward for you. You just have to look at how I did the other one. But I'll rather do the third one. Of course, it's also not that complicated, but let's do the third one. So the third one, okay, so I do the third one. I do the third one. And for the third one, if we take an element in G, then we know that then we have that the element and its inverse is equal to the inverse and its element, which is equal to the identity. Okay, so if we know that A is the inverse of A inverse, then the inverses are unique, and so we say that A inverse of the inverse is equal to A. So that is the third one, very, very straightforward. And the next thing that we deal with, is the integral exponent. Okay, this is 8.3. We do integral exponents of elements in a group. Okay, so the integral exponent of elements in a group. You should already remember we treated also examples of groups. So let's do this one. If we take any element in the group, so Solomon, so if we take any element in the group, then definition, we say that the zero exponent of the element is equal to the identity. 2, the m exponent is equal to n minus 1 exponent times a for n greater or equal to 1. And then 3, if we have a minus n, then we can write it as a minus 1 to the power n, also for all n greater or equal to 1. Right? So if you take example, if you take, if you have maybe J, you have a set of integers, and then you say 1, you take A to be 1. Okay, so example is let's J be equal to Z. Okay, let's take the integers. Then, or naturals, let's take the naturals. Okay, if we take the natural, then we know that 1 belongs to N. N, yes. And then we can check 1, or let's take 2. Better. 2. So first one, 2 to the power 0 is 1. So
Hello, sir.
Yeah.
Please, I wanted to share the screen, but it seems you've blocked the. It's not allowed. Who's disabled participants sharing screen?
You want to share which screen? My screen, or you want to share their screen? Your screen.
Your screen.
Can you see my screen?
Yes, please.
So you should share your screen from your side.
Yes, and then I use that one, and then what is telling me that host disabled participant screen sharing, or I should share mine rather.
Share your screen. If you share my screen, then nobody will have access to my work.
Okay, sir. Okay,
share
sir.
yours. You should share your screen so that what you are seeing, they should see it.
Okay, sir. All right, sir.
Okay. So then the second one is that if you take 2 to the power n, let's say n is 4. So if you take 2 to the power 4, it says that you can write this as 2, 4 minus 1 times 2, right? So this is 2 to the power 3 times 2. This is correct, right? Let's take n to be 4. Then this is correct. And the third one says 2 minus 4 to the power 4. We can write it as 2 minus 1 times 4 to the power times 4. And this is the same as this one. So this is what we are doing by the integral exponent of elements in groups. Okay. Then for that, of course, if we start doing this, we immediately see that we can manipulate this in several ways. So there's a theorem that says that if you let A to be an element, okay, an element of a group, okay, of G, of a set G, and you take M and N to denote, okay, to denote integers, then the following holds, okay, then the following holds. 1, a to the power n times a to the power minus n is equal to e, okay? 1, 2, a to the power m times a to the power n is nothing but a to the power m plus n. 3, a to the power m all to the power n is nothing but a to the power mn. Okay? So, of course, we can check. Let's check. We can just check this briefly. Example, take n to be 2, take n to be 3. Okay, n to be 3. Then let's check 1. 1, if a to the power 3 times a to the power minus 3 is nothing but a3 plus minus 3, which is a3 minus 3, which is a to the power 0, which is e. Okay. Of course, already here, I have already at this point, I have already used some properties. All right. But second one, if we take a and m is 2, and then a n is 3, then you say I have a 2 plus 3, which is a to the power 5. Salisu, I'm listening to you talk. Then the third one, a to the power 2 or to the power 3 is equal to a 2 times 3, which is a to the power 6. So this is an example that you can see of the application of this theorem. All right, so if you have raised your hand, I'm listening, just stop.
Yes, sir, please. I don't understand why a exponent n and a exponent minus n is giving us the identity, because the bases are the same. So why are we not adding the n and the minus n like we did for the second one?
Yeah, so of course, yeah, it's just a n plus minus n, which is a n minus n, which is a to the power 0, which is e. Of course, if you go back here, we already wrote this here, right?
Okay.
So we come back to the same point. All right, so again, we realize that we can also write again some other things here. That if we have a set G, if we have a set G, okay, if we have G, sorry, if we have G, okay, or such that you have two elements A, B belonging to G, then each of the equations, okay, each of the equations Ax is equal to B and Xa is equal to B has a unique solution, which is given by nothing but X is equal to A inverse of B, and the second one is X is equal to B of A inverse, okay? B of A inverse. So you can prove this very, very easy. Very, very easy. If G is a group, okay, suppose, okay, we are proving, so suppose J is a group. Suppose J is a group such that AX is equal to B for A and B in G. Then we can say X is nothing, because it's a group, we can always use an identity element, and then the identity we can always represent by inverse, okay? And then we can write its associative property as that. Then we know that AX is equal to nothing but B. So this gives us A inverse of B. Okay, so we have shown that X is nothing but is equal to A inverse of B, which is the first one. The second part, of course, you follow the similar trajectory and you are going to get the second part correct. So that's just a little bit introduction of groups. I'll go to rings now. But if you have any questions so far, you can ask. I'm going to talk, the next part I'm going to talk about is rings. And then after, I'll talk about fields. But after that, next week, when we meet, who's that? Who is that? finger. So these rings, we say that if we have a ring, then we need two operations, binary operations. So I write it as a set, okay, with two binary operations, or with two operations acting on it, okay? So we call it a ring. It's a ring if it satisfies the following axioms, okay? If it satisfies the following axioms. One is that you have that addition. So these operations, let me write, these operations, these two operations, addition and multiplication. So addition is associative. It means nothing but A plus B plus C is equal to A plus B plus C. Okay, for all A, B, C, I. Okay. 2. We say addition is commutative. Okay. Addition is commutative, and it means that A plus B is equal to B plus A. Then we have the additive element. Okay. The additive element, which says that if we have, we say additive element sorry, please mute. Additive element. So additive element, we say that A plus 0 is equal to 0 plus A is equal to A, of course, for all A in the set G. Of course, here too for all A, B in G, and similarly here A, B, C, all in G. Okay. Then the fourth one is that we have an additive. So this is the additive identity. Additive identity. Then we have the additive inverse. Okay. So the additive inverse is A plus minus A is equal to minus A plus A, and this is 0. Then we have multiplication associative, okay? Multiplication associative. And then the sixth one is that we have the distributivity or distributive, okay, property. Distributive property, that's multiplication is distributive, over addition. Okay, so These are the properties that you have to satisfy for the ring when you have these two binary operations and a set. So in general, you write a ring as here we have G and then we have plus and then this. So we need for a ring two operations, okay, on the set. For a group, we only need one binary operation on the set. Okay. So as an example, of course, there are several examples, but I'll just give you very straightforward examples. And then we try to also find integral expressions and stuff for this range. So let's go on. So here as an example, we say that the set, okay, Q is a rational numbers with its usual additions. So let me clean this, okay. So as an example, this guy here, we say it's a ring, this one. This is a ring and also can have the same Z as well. It's also a ring. And then you can have as well real is also a ring. So these are examples of rings. Okay. And by saying that it's a ring, it means that if you take example of if you take some rational numbers and then you take this binary operations of addition and multiplication, you should be able to check the axioms that we just spoke about, that they satisfy all those, and say that if they satisfy these conditions, these axioms, then it is a ring. Okay. So now we talk about the properties of rings. Okay. Properties of rings. One is that if you have A plus B, then you can say A plus C implies that B is equal to C. So I'm sure you saw similar properties for groups. Two, if we have A times 0, and then we have 0 times A, which is equal to 0 for all A in R. 3, we have A times minus B, which is equal to minus A times B, which is equal to minus AB for all AB in R. Okay. Then 4, the negative, okay, 4, the negative of A is equal to A for all A in R. 5, the negative of the sum is the sum of the negatives. Okay, then we have 6, the negative of the product is equal to positive. 7, the product and of the difference is equal to the difference of the product. And then 8, okay, 8 here is that negative 1 times A is nothing but minus A. And this we call the multiplicative identity. Okay. So, of course, you can prove all of these. We can do the proof one by one, but not interesting again because they follow the same thing. So we prove just one or two, or one particularly, and we say that if we consider A plus B to be equal to A plus C, then we can write B to be equal to 0 plus B, okay? And then we know 0, we can write it as minus A plus A, or plus B, and then we can write this as minus A plus B by associativity. And then with that, we know since A plus B is equal to A plus C, now we can substitute here, okay? We can substitute here A plus C, all right? And then we will get finally, we take this one, we take this guy, okay, we take this guy to the other side, then we have B plus A is equal to, so we have, let me write it well. We have A plus B is equal to A plus C, okay, which ends the proof that okay. Of course, the other way is you go also from the other side. Okay, so from here we see that B is equal to minus A plus C. Okay, and then if you go from the other side, you can also write it again as C is equal to 0 plus C. Okay, you can write C is equal to 0 plus C. Sorry, 0 plus C. And then this is also nothing but minus A plus C. And then you do minus A plus C. And then you know A plus C is the same as A plus B, right? So now you can also come here and say A plus C is equal to A plus B. So on both sides, you get the same result. So of course, you realize that when we did the definitions, or when we wrote the properties, also in this case, there was we didn't see one property. So here we saw addition associative, addition commutative, then we saw multiplication associative, but we didn't see the commutative part. So we go again to the commutative part in this case, okay, and that is on its own. So we say that there's a commutative and unitary rings, okay. In groups, we said abelian or commutative groups, and then in rings, we say commutative and unitary rings. What does it mean? We say that if let J be a ring, and I know what you now know that it is a ring, such that AB is equal to BA for all AB in R, we call J a commutative ring if the identity is also in R, is such that AE is equal to EA is equal to A for all A also in R. Then E is called the unitary ring. Okay, so this is how we define the unitary ring. Or E is called the unity, sorry. E is called, E is the unity, okay, the unity for the ring. And then we call it a unitary ring. Okay, so very, very simple to determine the commutativity or the commutative part as well. In that case, you need a ring that satisfies this condition, and then we need, you say it's commutative if this condition holds, and then E here is called a unitary ring. Example is that you can have Z, the integers, okay, or also the rationals, we say are commutative. Ring with unity 1. Okay, so there are several examples. So the second example of the ring of even integers. Okay. Even
Like past
even integers, okay, are also commutative rings. With no unity, okay. So these are examples of commutative rings. Then we make a theorem that says that if G is a ring, okay, that is G plus and times that has a unity element, then this element is unique. Okay, so if you have a ring that has a unity element, then that element is unique. So 9.3 is now we talk about multiplicative inverse. Okay, multiplicative inverse. So if we have a ring G with unity E, we say that X is a multiplicative inverse of an element A in R if A of X, X of A is equal to A. If A is in R, has multiplicative inverse. Then we will denote it by a minus 1. Okay, so this is what we mean by multiplicative inverse. If there is an x, which is the multiplicative inverse of an element a, then we know that the product of a and x is the same as the product of x and a. Should give it identity. And if a is a multiplicative inverse or has a multiplicative inverse, then we denote this multiplicative inverse by a to the power minus 1. Next one is zero division or zero divided. If we have G, okay, if you have a commutative ring, it's a commutative ring. If you take an element A in R, where A is not 0, then
Hey.
okay, where A is not 0, is the divisor in G. If there exists, okay, if there exists an element B also in G, where B is also not 0, such that A times B is 0. So example is that, I'm sure you remember your devices. So example, the element, okay, the element 2, 3, 4 are devices in that. Since you operate on 3, is 6, which is equal to 0. Okay. Next one that I talk about is the integral domain. A commutative ring with identity and zero and no zero divisors. Okay. It is a commutative ring so example, that is G plus times with identity and no zero divisors. No zero divisors. That's what we call the integral domain. Example, Z6 is not an integral domain. Since 2 and 3 are 0 divided in Z6. And generalize into a theorem. If we have A, B, are elements in an integral domain, D, such that A is not 0 and AB is equal to AC, implies B is equal to C. Okay. Then we say that if, however, we have a commutative ring, okay, sorry. It's a commutative ring with unity E such that the cancellation laws, okay, or the cancellation properties hold, then the set S is an integral domain. That is some little information on rings. Next, we talk about fields. So of course, next week we will do some other stuff that I've omitted as well. So fields, we say that if we have a commutative ring, you have a commutative ring S, okay, with more than one and having a unity so if a commutative ring with more than one element and having a unity, for every non-zero element in the set S has a multiplicative inverse in S. So commutative ring, multiplicative inverse, and then a unity. Okay. So theorem, we say that a field is necessarily really
Leave the meeting.
an integral domain. Okay. This is not very, the proof is like 3-4 lines. You should check it in the book. Then another important thing you should know in fields is that if we have an integer then the ring ZP of integers modulo P is a field.